Hi, I'm Steve Baird, and I'm going to be talking about three topics relating to a DO-178C tool qualification level 1 automatic model-based code generator. Number one, what is it? Number two, why would you want one? What are its benefits? And number three is the approach that AdaCore is currently taking in building one. So an automatic code generator is, as we've heard in earlier presentations, takes a model in the form of something like Simulink blocks or Stateflow and generates source code, for example, Spark or MISRA-C. And the question about, well, actually, strictly speaking, you can't say that it's qualified. We'll get back to that. There's a distinction between qualified and qualifiable, which I'll talk about later. But the idea is that you want this thing, in order to get tool qualification level 1, it has to provide evidence that it works the way it's supposed to, and that the translation correctly preserves the semantics. DO-178C defines several qualification levels for various tools, and we're talking about tool qualification level 1, which is the most stringent, and that's used in the case where the output is part of the actual airborne software that generate code, and that the potential consequences of a defective are potentially catastrophic. And so this is just the definition of the various qualification levels. So why would you want this? Well, it frees you up from a number of testing obligations, and testing obligations are expensive, as described in tables A5, A6, and A7. The idea here is that you can assume by construction that the translation is correct, as opposed to having to go back and sort of verify after the fact that the construction was correct. That verification process itself involves testing effort and resources. And then there's always the possibility that you'll uncover a problem, which it might be a problem in the translation, or it could just be a limitation of the tool or something, and then you have to have a workaround. In any case, discovering that you have to change your model input in order to cope with a problem with the tool late in the game is something you want to avoid. As has been mentioned, the earlier you can find problems, the better, and better in terms of dollars. Now, just to talk about the context here, DO-178C defines, and this is sort of an excursion off. This is just some of the things that were not addressed in the earlier DO-178B, but now we have supplements that specifically talk about software tool qualification considerations, model-based development and verification, object-oriented technology and related techniques, and formal methods, and in particular the interactions between formal methods and testing requirements. So this sort of is the context that we're talking about. And so TQL1 lets you assume that the translation behaves as it's supposed to with respect to coverage requirements, no unintended functionality, or and the usual sorts of things that you'd want. And so if you have this, you remove some testing requirements, some testing obligations, and that's a good thing. Now, I said earlier that there was a distinction between qualifiable and qualified. You don't actually qualify a tool. You qualify a tool and its use in the context of a particular DO-178C certified project. So what actually happens here is that the tool vendor, in this case AdaCore, would provide a qualification kit, qualification materials that can be used to obtain qualification, and then there's still a little bit of work that's required on the part of the user to ensure that the way that it's being used in the context of that particular project is consistent with the requirements of DO 178C. But the idea is that that's a relatively small amount as compared to the fairly large amount of effort required to actually do the that's embodied in the qualification kit. So how do we do it, or how will we do it? QGen is Adacor's automatic code generator. It takes a Simulink or Stateflow blocks as inputs and generates source code. And the point here is, from the point of view of looking at it with respect to qualification requirements, is it's big. It's got 50,000 lines of handwritten code and another 50,000 lines of machine-generated code. And that's a lot of code for something that's going to require essentially something similar to DO 178C certification as far as rigor and testing requirements. And DO 178C defines tool operational requirements and then lower level tool requirements, which are in many ways analogous to the high-level requirements and low-level requirements that would be used to specify the application itself. It's a very similar structure. And so to cope with this, if you just look at the input model and the target language and try to go directly from one to the other and define your requirements in terms of that, that's too complex. And so instead, we introduce an intermediate representation called P, and this is common in many compiler translation type things where you take your input and you map it into an intermediate representation, then you perform so that's one semantics preserving transformation, and then you perform transformations that map that intermediate representation back to the same intermediate representation, and that's a second kind. And then you finally generate your final output, and compiler, which is the third sort. And so compilers have been organized this way for years. And so we introduced three kinds of requirements corresponding to these three sorts of semantics preserving transformations. And so you have the type ones, which refer to taking the model-based input and generating the intermediate. And then there's actually two kinds of intermediate to intermediate transformations. There's the ones where optimizations, where you're generating, improving it, and then there's the expansions where you have a more complex construct and then you express it as a composition of simpler constructs. And the line between those two is maybe a little bit blurry in some cases, but that's okay. So you have these three different kinds of requirements, and that gives you the structure that you need for approaching the problem as you're going to define a number of semantics preserving transformations that eventually are going to get you from the desired input to the desired to the source code output, from the model input to the source code output. But each step is of manageable complexity. And that's, so for example, well, this is essentially saying the same thing, that we have this intermediate representation, and which is independent of both the details of the model input and the and the source code output, and it provides, for example, genericity dealing with things like a block, which might take, the same block might take a scalar, or it might take vectors, or the same type of block, and this copes with that issue. So we get these high-level requirements, that go between, and as I said, there's the transformations from the input model to the intermediate, and from the intermediate to itself, and then from the intermediate to the target language, which would be Spark 8 or Mizra C probably. And we have high-level specifications for each of these. And then these get mapped. So here's an example of a type 1. This is a saturation block is one particular kind of block that takes as input a value and then limits, and then it either returns its output would either match the input if it's within the limits, or if it's not, then it would be the value of the corresponding limit. And this is just an example of the kind of requirement that we might generate for that particular block. And part of that is legality checks, so that you get model checking, and then part of it is a specification of what the generated P, what the intermediate representation generated for this particular block might look like. And this is dealing with the scalar case, and then dealing with the vector or matrix cases. So this is this is just to illustrate the kind of requirements that are used. And then here's one for type 2 where we're doing a transformation from the intermediate to the intermediate. And this is talking about when you're dealing with vectors and matrices and introducing an explicit loop as opposed to having it implicit in the fact that you were using a matrix or a vector. And this is the sort of semantics. So these are, again, this is just an example of the sort of high-level requirements that would be generated for this sort of thing. And here's an optimization example where we could have a requirement that if it's never read, then you eliminate a variable, or if it's only assigned once, then under certain circumstances, it's safe to replace all uses of the variable with uses of the right-hand side of that one single assignment. And then here's an example of the third category where we're generating source code. It says if the P looks like this, then the generated C code would look like this. And so these are just the sort of requirements, and here's just a summary of how you might specify the requirements for the various phases and the transformations. But the point here is that we just have a sequence of semantics preserving transformations that eventually will get you from the input to the desired output. Then we get the tool requirements. Remember, these are the lower level requirements that correspond to the higher level requirements. And so here's just an example of some of the lower level, some of the requirements, the low level requirements associated with the saturation block operational requirement that we looked at earlier. So we get two kinds of test cases. There's the ones where the input is the Simulink model and the output is the generated source code. And those you can test using conventional techniques fairly easily because it doesn't require any knowledge of the internal implementation. You can view the code generator as a black box and just either inspect the generate code or execute it and see if it does what it's supposed to do when it's, but the point is that there's no knowledge of the internal implementation required. The more interesting case, so that's table T6 objective 1 and 2. The more interesting case, or at least, anyway, another case is the case where your requirement involves this intermediate representation, and the P, and there you have this. You can't use the same techniques. Your input isn't something that's visible to the user, and if in the case where the P is input, and similarly if the P is being generated as output, then again you have the same problem. And so you have requirement-based testing, but it's based on an internal context, and this involves state that's normally not made visible. So it's fairly straightforward in the case where the black box approach works. Again, you have all sorts of problems in addition to what I already mentioned. There's traceability issues and coverage issues, and expressiveness, because there's no good way to talk about this internal state. And so just to summarize, here you'd have your type 1 transformations in the first oval, and your type 2s in the second, and your type 3 in the third. And the integration testing sort of corresponds to the ones where the black box approach works. And the input is the model, and the output is the source code, and you're not talking about the intermediate stuff at all. And those, your user language has a good editor for if there's a particular set of input that you want to test, it's easy enough to craft it by hand. The user language is simpler and has a higher abstraction. Coverage is tougher precisely because of that higher level of abstraction. But the corresponding problem with unit testing is the unit testing approach is that there's no editor for this P intermediate language. It's complex and has rules that weren't really intended for exposure to users, and it's hard to achieve this with no. You can get exhaustiveness precisely because it's isolated. It's just more like unit testing, but. So the approach that we're taking is essentially building unit testing into the product itself. We're going to, for each test, you define a predicate that says whether or not this particular input to a given subprogram is an instance of a particular test case that you're interested in. And then in the case where it is, you define a way of defining the expected output, the validity of the output. And this could be either computed on the fly, or it could be reading it from a file if you have a pre-computed expected baseline. But the idea here is that you're going to instrument the code of the tool so that at execution time, you log the occurrences of the test cases and then check the expected result. And so you don't have to write unit tests per se. You just run the tool over a large number of cases, viewing it as sort of a black box, and then at the end you see which test cases have been exercised and what the results were. So here's slightly more detailed, just saying that upon entry to a given subprogram, you test to see if this is an instance of a test case that you're interested in, and if so, then at the end, when you exit, you check the result that was actually obtained with the expected result. And all this instrumentation code is marked as ghost code, which is it's a code that can be easily disabled, and so that you're going to generate the normal when you're not trying to generate qualification materials. You wouldn't be running a version with this ghost code, and ghost code's more interesting in Spark, but that's a side topic. So here's an even more detailed example of the same thing, where you're testing to see, upon entry to the subprogram, you look to see if it's one of these test cases, and if so, then you note the fact that it's been covered and log it to this log package, which has state and which is not part of which is ghost code. So it's only there in the case where you're using the instrumented version of the tool. And then upon exit from the subprogram, you test, as you say, if indeed we did cover this case in this case, then compare it with the expected results and log the results. So for example, and here's an even more specific. So here we are, this guy's job is to remove go-to blocks. And so upon input, it says if there was in fact at least one go-to block, then we'll note that we've that this is a test case that we're interested in, and then upon exit, and this is one where we compute on the fly the expected post condition, which is that the go-to blocks have been eliminated. And again, you can have more than one. It's sort of for each test case of each low-level requirement, of each high-level requirement, as it applies to each transformation. But the point here is that you're building unit testing into the code. Again, you can. It doesn't have to be computed on the fly. You can read it you can read your expected result from a file if that's what you want to do. It's a very general thing. A lot of cases it's done using this test case construct. But this is an example, this is an example for a square root function where we have one test case named TC1 that's the case where x is equal to 1, another test case where it's greater than 1, and then we would, whenever you call this function, the appropriate logging would take place to indicate whether that test case has been covered. And now, and there are other ways to do it. You don't have to use that particular construct, but the point is that you use, or a point is that you use ghost code throughout, so that it all disappears when you're not generating qualification materials. But you have this state package, and so here's an example of summary where you've done this testing and you have the first class of transformations in the blue oval, and the second class of transformations, the P to P, in the second oval, and the third class of transformations in the third, and so for a given test case of a given unit test requirement of a given transformation, you might get a log of which ones got exercised, and which and then of those, how did they pass, did they fail, and so so the idea here is you're using integration testing techniques. You're able to view this as a black box without delving into the internal implementation in order to accomplish unit testing. That's sort of the, you have a multi-pass structure of the code generator, just like many translation and compilation type tools. And your requirements match that structure. You don't want to have to expose the internals, so instead you use this technique to build unit testing into the code, and now you can use integration testing to accomplish unit testing, and that's really the key idea. And you could use the same approach in other multi-pass tools. It happens that we're using it in this case. Any questions? And we expect to have an example in 2018. We expect to have TQL 1 qualification. Okay.